Okay, and finally, let's wrap up the whole lecture. In this lecture, we learned the notion of a second-order linear ordinary differential equation, and we have the existence and uniqueness theorem for solutions of a second-order differential equation. The most important thing here is that the kind of what is different as compared to first order is that the there is this extra condition that the initial condition is not only the initial condition for the value of the unknown function, but also the initial condition for the value of the first derivative of the unknown function. So this general existence and uniqueness of Picard-Lindelof theorem is the only thing that we know so far about the general second order differential equation. So actually either linear or non-linear, because if it is linear, then the advantage as compared to the non-linear case is that for linear differential equations, the domain of solutions is also the same as the domain of the coefficients of the differential equation. But for a non-linear case, the domain of solutions may be smaller than the domain of the right-hand side. Then we did not prove the existence and uniqueness theorem. Well, specifically, we did not prove this part about the domain for linear differential equations. But so I guess you'll just have to believe me, or you can try to find the proof somewhere online. But we applied this Picard-Lindelof or existence and uniqueness theorem to prove the structure theorem about solutions of a homogeneous ordinary differential equation. Yeah. And here is the most general form of a second-order linear homogeneous ordinary differential equation. And the structure theorem tells us that the set of all solutions forms a two-dimensional vector space. Well, then for your information, a basis of the space of solutions is also called a fundamental set of solutions, which I personally don't like, because a fundamental set of solutions is just the same thing as a basis. So why bother inventing another name for the same concept? But historically speaking, the concept of a fundamental set of solutions appeared first, and then mathematicians kind of generalized it and developed a general theory of vector spaces from a theory of solutions of differential equations. Well, but it was a long time ago. But now I think we should have abandoned the term fundamental set of solutions, because it's the same thing as a basis. But if you read a textbook on differential equations, you will probably see this fundamental set of solutions. So please just know that it is the same thing as a basis. Then equivalently, given any two linearly independent solutions of a second-order differential equation, the set of all solutions is given by as linear combinations of these two linearly independent solutions with some coefficients. Well, and to check if two given solutions are linearly independent, we compute the Wronskian, right? And either the Wronskian is constant 0, so the Wronskian is a function of t, so it may be constant 0, then the solutions are linearly dependent, or is never 0, so it's always positive or always negative, then linear independence. There is no method to solve general, even homogeneous linear ordinary differential equations second order with non-constant coefficients, and not only we don't have, but I don't think that there is a general method. Well, but if coefficients are constant, then in order to solve the equation, the differential equation, we need to set up the characteristic equation, and we need to solve this characteristic equation, right? So if the roots are real and distinct, good, then there is a formula to produce solutions of the corresponding differential equation. Well, but if we have a multiple root or complex roots, then we don't know yet, and it's going to be explained in the next lecture.